Okay, so welcome to our week 6 class meeting. I appreciate you all coming today. So in week 5, we started a 2-week section on probability. And this week, week 6, we are finishing up that section. You may have noticed that the formulas in week 6 get a little bit longer than they were in week 5, but later in the presentation today, we're going to go over how to use a calculator that is going to be helpful to take away some of that work that you're doing by hand. So if you haven't already, please go ahead and open up that web calculator. I posted the link. It's right here on the page that says Math 130 week 6. I think you should be able to click on that link and launch it. If not, I did put it in the chat, so you can click on that. If you just scroll to the top of the chat, the link should be there. Okay, so if we're ready to go, I'm going to stop sharing this and start sharing my screen. Okay, just a quick check. Everyone can see the screen. It's the start of the slides, and I'm going to go to the first slide that says last week independent events. Everyone can see that? Perfect. Okay, so as usual, I'm going to minimize the chat. So if you have a question, just hang on to it. We'll pause every few minutes for questions at every few slides. Okay, so last week we talked about independent events, and we remember that when you have two events that are independent, that means the outcome of one does not affect the probability of the other. We had this formula right here. When we had the probability of A and B, that means the probability that those two events occur at the same time. All we had to do was multiply the two individual probabilities, and that was it. But that was only for when the events A and B were independent. They could have been dependent, right? And if you remember last week, I told you that this week we were going to talk about what the formula is when those events are dependent. So when events are dependent, that multiplication rule just changes slightly. Just as some examples of what dependent events are, just to refresh ourselves. So one example of a dependent event, or two dependent events, are the probability that you are pregnant is dependent on whether or not you are a man or a woman, right? If I just asked you, what is the probability that someone is pregnant, you might be able to give me a number based on some research. But if I changed the question and I said, well, wait a minute, given the fact that it's a man, now what's the probability that the person is pregnant? Now all of a sudden the probability has changed, right? Now you know that the probability is 0 because I told you that it was given that the person I was talking about was a man. So those two events are dependent because the fact that I knew that it was a man changed the probability that the person in question might be pregnant. Likewise, the probability that you can reach the jar on the top shelf is dependent on your height. If you're very short, you probably don't have a very good probability of being able to reach something on the top shelf. If you're very tall, like I am, then you probably have a good chance or a high probability of reaching things on the top shelf. It's funny when I go to the supermarket because little old ladies will come up to me all the time and ask me to reach the crackers or the soup or whatever it is on the top shelf, because I have a high probability of reaching it and they do not. Yes, Raquel understands exactly what I'm saying. Okay, so like we said, that formula from last week is going to change slightly when the two events are dependent. So this is the new probability. What we read this as is the probability of A and B, meaning those two events occurring at the same time, is equal to the probability of A times the probability of B given A. So this notation right here, the B with the little line after it and then the A, means the probability that B occurred given that A occurred. I saw a note that I'm echoing. Am I echoing for everyone? Janet, it sounds like it might be on your end. You might want to try logging out and logging back in. That might fix it. Or just give it a second. Sometimes it acts weird for a minute and then you'll be okay. Okay. So like I said, that little bar between the B and the A means that symbol can translate in English to the word given. Whatever event comes after the bar, that is the event that is given. So we know that that event already happened. So given the fact that it happened, now what is the probability of the other event B occurring? So there's two ways we can see this equation. So the first one is what I already typed, probability of A and B equals probability of A times probability of B given A, or we could just do a step of algebra and switch it around so now it looks like this. So now the probability of B given A is isolated, it's all by itself, and the other two probabilities are in the expression. So this formula, this second one, is a very good formula to know, but you have to be careful that you're putting the correct probabilities in the correct place. In particular, this denominator right here gives people a lot of problems. So remember this, the event after the bar in the given portion is the same event that should be in the denominator. Okay, just remember, after the bar equals under the bar. So whatever event comes after the bar in the given statement, that's the event that should be in the denominator on the right hand side. Okay, so there's a few different ways on the homework that you might see a question that talks about dependent events and is using those formulas from the prior page. You could have just a formula problem where you're just going to apply the formula straight out. You could have a problem that uses a table where you need to extract values from a table, or you could have a word problem, which is everyone's favorite. So let's just do a couple examples, one of each of those. I'm going to hop over to another screen and grab my pen. Okay, now I'm using my drawing tablet here, which usually works, but sometimes is weird. So let's see how this goes. All right, so I want my pen. We'll do it in blue. Okay, so here we have a statement. Let's see if I can get this to work. There we go. So it says, suppose that E and F are two events. Probability of E and F equals 0.2. Probability of E equals 0.4, and we want to know the probability of F given E. So by that formula on the other side, on the other slide, probability of F given E is equal to the probability of F and E over the probability of E. Remember, the event that comes after the bar is the event that goes in the denominator. So E came after the bar on the left, so E should go in the denominator on the right. And then from there, all you have to do is plug and chug. So the probability of F given E is going to be equal to probability of F and E was 0.2, right? Probability in F and E is 0.2. So all I have to do is put on the top is my 0.2, and the probability of E was 0.4. So at the bottom, all I have to do is put in 0.4, and then we're all just going to grab our calculator, and if we type in 0.2 divided by 0.4, we're going to get 0.5. So the probability of F given E using this formula is 0.5. Any questions about how to use the formula? Okay, let's try an example that uses a table. So here we have this table, and it's giving us a couple different things. It's giving us some numbers for males and females, and then it's giving us numbers for different age ranges. Okay, now if I look here at the question, it says, what is the probability, I hope you guys can read this, it looks a little blurry to me. What is the probability that a randomly selected driver fatality who was male was 21 to 34 years old? Now, it didn't say here anywhere in this question specifically the word given, right? It gave us two events, the event that the person is male and the event that the person is 21 to 34 years old, but I don't see that word given precisely here. So sometimes that word is not going to be provided, and we just kind of have to interpret it. So what do you guys think? Which of the two events here is given? Is it given that the person is a male, and given they're a male, we want to try to find the probability that they were in that age range? Or is it the opposite? Is it given that they're in that age range and we want the probability that they're male? Which one do we know? What is given? Yes, we know that the person is male. So it says right here, selecting a driver fatality who was male. So we know that the person has to be male. That is not, there's no flexibility there. The person has to be male. So what I can do is I can come over here to my chart and I see this whole row for females. Well, if I know that it's given that the person is male, I don't even care about this column. Maybe I'll use it for another part of the problem, but for this problem, if I know the person is male, the female column has no interest to me for answering this. Okay, now remember what we did last week when we did probabilities. Probability is always a fraction. On the top of the fraction go the number of people or things that are what you want, so that meet the criteria that you've set forth, and the denominator is the total number of things. So what is it that we want now from this column? What's our criteria that we're looking for in this male column now? Yes, it's that age range, right? It said driver who is male and was 21 to 34 years old. So when I set up my probability here, the top of the fraction had better be the number of people that fit that criteria. So how many people were there that fit that criteria from the table? Yes, it was this one right here, right? This is the number on the row for the 21 to 34 age range. So that number, 14,196, is going to go up at the top. Okay, now on the bottom of the fraction for probability should go the total number of people or things. So do I have that number here in the table, or could I get it from the table? How did you get that, James? Yes, Raquel. So we need to add them all up. Notice there is no row there for a total, right? The total was not given, but we can add them all up and we can get the total no problem. So James says that adding these up, we get 39,337. Anybody get anything different? I did not throw it in my calculator just yet. James, we're trusting you. Yes. Oh, you get a 5? Okay, let's check. So we're going to do 189 plus 5046 plus 14,196 plus 12,859 plus 4502 plus 2543. Okay, I do get a 5. No problem, James. I think we've all been there and added something wrong in our lives, so you are okay. All right, so that's it. So that's our probability right here. And if we go ahead and we type in that fraction to our calculator, what do we get for the probability? Get 0.36. So the probability that a random selected driver who was male was 21 to 34 years old is going to be 0.36. And just to note, if we wanted to write this with the notation, we could write it like this. The probability that someone is 21 to 34 years old, given that they were male. That's what it would look like in notation form. Okay, any questions about the table problem, how we got those numbers, that notation that I just wrote down, or anything else about this problem? I see typing, so I'm just waiting for the typing. Why is the notation reversed? Reversed how? So the event that's given always comes at the end, after the bar. So we knew that it had to be male. The fact that it was male was given. So whatever is given always comes at the end. So that's a good point. It might come out of order to this notation in the wording of the question. So you do have to interpret it correctly. Okay, any other questions about that or this question? Okay, let's do one more. So this is our word problem, everyone's favorite. Gosh, this looks blurry on my end. I'm going to go ahead and read it. I hope you guys can see it. So it says, suppose you just received a shipment of 12 televisions. 2 of the televisions are defective. If 2 televisions are randomly selected, compute the probability that both televisions work. That's the first question. And then there's a second question that says, what is the probability at least one of the 2 televisions work? So let's do the first question first. It says, if 2 televisions are randomly selected, compute the probability that both televisions work. So this is how I like to set up these problems. So I'm going to select 2 televisions. So I'm just going to make 2 little lines for myself just to indicate that I'm looking at the first television and then I'm looking at the second television. So here's my first television and here's my second television. Okay, let me get a different color here to do the rest of this. All right, so let's think about my first television. I don't care about the second television right now. So for the first television, again, there were 12 televisions total and 2 of them were defective. So what is the probability that on my first selection, I select a television that works? So again, there's 2 that are defective. So that means defective means they do not work. So what's the probability that I select one that does work? James has got it. It's 10 out of 12. So there were 12 televisions total. If 2 of them are defective, that means 10 of them are not defective, right? 10 of them work. So you got to pay very close attention to the wording of the question because you don't want to accidentally put in the complement or like the opposite of what it's asking for because they provided you with some numbers in a different way. So be very careful with that wording. Any questions about why it's 10 out of 12? There's 12 TVs, 2 are defective, so 10 are not defective, they work, and we wanted to select a working television for the first one. I see typing, so I'm just going to pause for a second to let you finish typing. Are we supposed to reduce the fractions all the way through? You can if you want to. The most important is that you reduce your final answer before you put it in. So you could reduce here if you wanted to, if it makes it easier for you. I like to put it in the way that it's stated for this portion of the work because that way I don't have to keep in mind like, oh, where did this 5 come from? Oh yeah, I reduced. Like I can look and just say, where did this 10 come from? Oh yeah, there were 10 working televisions. So to me it's more intuitive to keep it in the numbers that correspond to the question at this stage and only reduce at the end. But you certainly can reduce here if you want to and it won't change the outcome. Okay. So that was for our first television. Now let's suppose that I made my first selection. I selected a television. I determined that that television was working. So now I've put that television aside. It's not in my sample anymore. I've put it off. I hooked it up in the living room. So now I'm on my second television. So now that I'm on the second selection, how many total televisions are left? James, you are so fast. Yes, there are only 11 televisions left now, right? So my total in the denominator is going to change to 11. How many of those televisions are working? There are 9 now that are working because there were 10, but then I removed one, so now there's 9. So on my first selection, I had a 10 out of 12 chance of picking a working television. Now, given that I picked a working television on my first selection, then on my second selection, now I would only have a 9 out of 11 probability. Now, what do we do with these two numbers to get our final answer? Did our formula say to do? Yes, we're going to multiply. We will reduce at the end if we need to, but what we have to do here is multiply. Remember, it was probability of E given F is equal to, right? I'm sorry, that's not what I wanted to do. Whoops. Probability of E and F is what I meant, equals probability of E times probability of F given E, right? Okay, so we are multiplying here. We're always multiplying. So we're multiplying right here. Anybody have the answer? James does. Good job, James, and good job, Janet. Yes, so it is 0.68. Okay, so this was the probability of getting 2 working televisions. Okay, any questions about that? Now, the second part of the question said, what is the probability that at least one of the 2 televisions work? Now, do we all remember the rule about at least one from last week? Remember, probability of at least one whatever is equal to 1 minus the probability of no or none of that same whatever, right? That ring a bell for everyone, I hope? So if we want the probability that at least one television does not work, that should be 1 minus the probability that no television does not work, right? We fill in the same phrase on both sides. Well, this side here, right here, probability that no television does not work. Now, that's a terrible sentence in English with the double negative, right? What's an easier way to say that no television does not work? It means that they both work, right? Well, do we know the probability that they both work? What is it? Yeah, it was this one, right? This was the probability that 2 televisions work. This phrase right here is the same thing as saying they both work. So the probability that at least one does not work should be equal to 1 minus 0.68. Okay? That makes sense? So that's going to be about 0.32. So the probability that at least one of the televisions does not work is 0.32. Any questions about that? Either portion of the problem. The 0.32 is from 1 minus 0.68. No, not duh. It's good to ask. No point in not noticing it and then being confused about it. Yeah, just the 1 minus 0.68. Other questions about this problem? Homework has us go out further and answers change. I'm sorry, Janet, I didn't understand. Like further how? Further in the decimals or? That's okay. I was just being a little lazy here and to save space just to get the point of the formulas across. You just do however many decimals the particular question asks for. Any other questions about this or any of those 3 examples? Okay, so if you understood those, then you should be okay on the homework because that's basically the 3 different types of formula that you're going to have vis-a-vis the dependent probabilities. So now that we've done dependent probabilities, let's go ahead and talk about counting. This is the topic where the formulas get a little more gnarly, but like I said, we're going to go over how to do this in the calculator in a few minutes. So James, I think you were the one that said you missed StatCrunch, so we're not going to use StatCrunch for this, but it's going to be just as easy, possibly easier. Okay, so sometimes we need to figure out the number of ways we can gather a group of things from a larger group of things. So for example, Baskin Robbins, anyone, I think Baskin Robbins is nationwide. Is it? Actually, I'm not sure. Anyways, Baskin Robbins, if anyone doesn't know, is an ice cream shop, and they have 31 flavors of ice cream. So maybe I want to know how many different ways I can get 2 scoops of different flavored ice cream in the 2-scoop cup or the 2-scoop cone. Likewise, say there are 10 students in a club and they need to select a president, a vice president, and a treasurer for their club. So maybe I want to know how many different ways are there for them to select those 3 officers for their club. These are different ways that I can count up the number of ways I can do something like that. So again, if you don't already have it, please have open the Web 2.0 calculator, because that's what's going to make the work on these kinds of problems infinitely easier this week. Okay, so even though we're going to be using the calculator, let's make sure we know what the calculator is doing for us. So what's a factorial? So a factorial is just a mathematical operation. It's denoted by a symbol that looks like an exclamation point. You know, you have lots of symbols that tell you what to do with numbers, right? You have a plus sign, and you know that when you see a plus sign, that means you add the 2 numbers between on either side of the plus sign. You have a subtraction symbol, you have a division symbol. You know what all those symbols are telling you to do with the numbers. So the factorial is just a different symbol telling you what to do with the numbers. And what it's telling you to do is it's telling you to take the number that's in front of it and to multiply that number by every positive whole number less than it. So for example, if you have 5 factorial, what you're going to do is take 5 and you're going to multiply 5 to every positive whole number less than it down to 1. So 5 times 4 times 3 times 2 times 1. And you would get 120. So 5 factorial is equal to 120. 3 factorial is equal to 3 times 2 times 1 is equal to 6. 200 factorial would be equal to 200 times 199 times 198 times 197, etc., 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 all the way down to 1. And I challenge you to find a calculator that will do that for you, because I put it in my calculator and I got an error. So these factorial numbers get really big really fast. Notice right here I did 3 factorial and I got a value of 6. And then I just went up 2 numbers, just up to 5 factorial, and all of a sudden I was at 120. So just 2 digit changes in the factorial number shot this up by a lot. And by the time I get to 200 factorial, my calculator can't even do it anymore. So these can get big really, really fast. Just a note, fun fact, so 1 factorial is 1, and believe it or not, 0 factorial is also 1. So if you ever see either of those in a problem, or if you want to impress someone at the bar, make sure you tell them that 0 factorial is 1. They will be impressed for sure. Okay, so on the Web 2.0 calculator, you can do the factorial just by typing the number and then the exclamation point on your keyboard. So just give it a try. Have that calculator open. So see if you can do 6 factorial in the Web 2.0 calculator, and then post what you get. Again, do not do 6 times 5 times 4, etc. Do 6 and the exclamation point and hit enter. Thanks, James. I didn't see your note, but yes, it is available on your phone also. You can browse to it on your phone also if you don't want to download it for some reason. So lots of options here. It's not on the calculator. You type it on your keyboard. So just like how you would type it if you were typing a sentence and you wanted to type an exclamation point, it's probably on the 1 key. Everybody got it? So it's literally like you're typing an exclamation point in a sentence. Yes, so we're all getting 720. Good. Excuse me. So 6 factorial is 720. Okay, any questions about that or how to get it on the calculator? It's that easy. The number and the exclamation point. All right. So the way we count things up, we can do it in two ways. One is called permutations and one is called combinations. These are two ways to count how many ways we can select a certain number of things from a larger group of things. In permutations, the order matters. And in combinations, the order does not matter. So what that means is if you are selecting things and the order in which you select them matters, so if you select A and then secondly select B, that is a different combination than selecting B first and then A second. If selecting them in a different order gives you a different outcome, then you have a permutation. If selecting them in different orders does not change the outcome, then you have a combination. I know that's a little weird to just hear it, so let's do some examples and see if it makes more sense with examples. So say you had a group of 10 students and you needed to select a president, a vice president, and a treasurer. So in this case, the order matters because if you select Mary to be president, Tom to be vice president, and Ralph to be treasurer, that is a different selection of officers than if you have Ralph as president, Mary as vice president, and Tom as treasurer. So notice it's the same three people that you selected, but since you selected them in a different order, the outcome changed and you had a different event. So since the order mattered, that means this is a permutation, okay? So now let's say that from a group of 10 students, you need to select a committee of 3 people. So they don't have rankings. It's not a president, vice president, treasurer, or any other kind of ranking. You just need to pick 3 people. So in this case, the order does not matter because if I select Mary for the committee and then Tom and then Ralph, I still have the same committee as if I selected Ralph first and then Mary and then Tom. Since there's no differentiation between the positions on the committee, those two are the same event even though I picked them in a different order. So since the order didn't matter, this is a combination, okay? Any questions about those? Okay. So let's give it a try. So say we're at Baskin Robbins. You can tell I like ice cream. And we have 31 flavors to choose from. And we need to select 3 flavors for our banana split. Now, do you think that we should be working with permutations or combinations? Does the order in which I select my flavors change my banana split? If I select vanilla and then chocolate and then strawberry, is that a different banana split than if I select strawberry, then vanilla, then chocolate? Yeah, this is going to be a combination because the order does not matter. Okay, let's try this one. So there are 7 runners competing in the 100-yard dash in the Olympics. 3 of them are going to receive a medal, gold, silver, and bronze. So in this case, does the order matter? Yes, in this case, the order matters, right? Because whoever gets gold, whoever comes in first gets the gold, and that's the most prestigious, right? Whoever comes in second gets the silver, and whoever comes in third gets the bronze. So if I change the order, then the winners are going to change, right? I bet the guy who goes across the finish line first and gets the gold, if I gave him the silver, he would probably not be happy, right? Because the order matters. So since the order matters, this is a permutation. All right, any questions about permutations or combinations before we talk more in detail about permutations? Okay, so in permutations, again, the order matters. Now, this is the formula for permutations. If I want to select R things from a larger group of size n, I write the notation as a little tiny n on the left-hand side of a capital P and then a tiny little r. So the n is representing the total number of things I have to choose from, and r is representing the number of things that I want to choose from that larger group. And this is the formula right here. the permutations NPR is equal to n factorial divided by n minus r factorial. So let's just see an example of how this would work out if we were doing it by hand. So same example as on the previous page. There's 7 runners completing in the 100-yard dash. 3 of them are going to get a medal. We agreed that was a permutation. So the total number of things is the total number of runners, which is 7. So that's going to be the N. The number that I'm selecting is going to be 3, the number of winners who receive a medal. So that is the R. So I set up in the formula 7p3, and I would get 7 factorial, because that's where the n goes, over 7 minus 3 factorial. So this is how the work would look if we were going to do the whole thing out. So first we would simplify by the order of operations that expression in the parentheses at the bottom. 7 minus 3 is 4. Now remember, the factorials mean that I'm going to take that number and I'm going to multiply it to every single number less than it. So on the top where I have 7 factorial, I have 7 times 6 times 5 times 4 times 3 times 2 times 1. And on the bottom, I have 4 times 3 times 2 times 1. Now, if you remember how to cancel things in fractions, if you're multiplying on the top and bottom of a fraction and you have a common factor in there, you can cancel it out. So notice on the top and bottom we have a 4, top and bottom we have a 3, top and bottom we have a 2, top and bottom we have a 1. So those can all actually cancel out, and we'll just be left with 7 times 6 times 5 is 210. So there are 210 different ways for those medals to be awarded. Good job, James. James, you get the gold medal. Okay, so I know we all had fun doing that by hand. So now let's see how we can do it on the computer. So yes, the calculator is great. So everyone please get the calculator open if you haven't already. So if we're going to do 7p3 in the calculator, it's going to go like this. So first type the number 7. Then there should be a little button. It's down kind of on the bottom left, and it says NPR. Click that button, and then type the number 3. So it should look like what you see right here on the screen before you hit enter. Okay, it looks like this, NPR and then 7-3. You don't have to type it like that. You just type 7, then the NPR button, and then 3, and then it's just going to format itself to look like that. Now, the reason I like this calculator is because look up here at the top. It actually created this formula, right? So I can look at this formula and I still know that it's applying, whoops, didn't mean to do that. It's applying this formula up here. And then if you're here and hit enter or equals, then it's going to give you the number right here. Did everyone get 210 doing the steps that way in the calculator? Everybody cool with that? Looks like everyone's saying yes. Anybody have a problem with the calculator? Go ahead and type in if you had any issue with that or if it didn't work for some reason. Yes, no, this is definitely faster. I would do this unless you receive some joy from doing it the long way. Where was this in high school? Yeah, most calculators actually do have this button, but we may as well use one that's free. And I like this calculator, and this calculator is going to be really helpful in week 7 and 8, so I think it's a good idea to start getting used to it now. Any other questions or issues or anything else about permutations or this calculator? We good? I see typing, so I'll go ahead and pause. So you need to make sure you understand where the numbers need to be. In the formula, yeah, so basically the bigger number is always going to come first because that's the total number you're picking from, and then the smaller number, the smaller group that you're choosing, always comes second. So it's always biggest number first, smallest number second. And yes, in the formula it matters. So like if you accidentally switched these, if you switched the 3 and the 7, it would get all messed up because then you'd have a negative number in here and it would be all bananas. So just remember, bigger number first, smaller number second in the calculator. Any other questions? If you did switch and got a negative number, is that an indication something went wrong? Yes, you should not have a negative number when you're doing any of these counting formulas. So if you're using the calculator, then the negative number shouldn't come up at all because you're just going to type in the 7 and the 3. So it shouldn't come up, but yeah, you shouldn't be taking a negative factorial ever. Any other questions before we keep going? Looks like no, so I'm going to keep going. Okay, so let's give it a try now. So we're all by ourselves. So we have the NPR formula that we just talked about. So now we have a group of 10 students, and we're going to select a president, a vice president, a treasurer, and a secretary. So first of all, does the order in which I select these students matter? Yes, it does, right? Because if I select Mary as president and Tom as vice president, that's different than Tom as president and Mary as vice president. So yes, the order definitely does matter. So what is the total number of things we have to pick from here? Yes, there are 10, right? There were 10 students total in the group. What's the total number of things that I need to pick? How many? There's 4, right? President, vice president, treasurer, and secretary. So I need to pick 4 things. So in the calculator, I would need to do 10p4. So go ahead and give it a try and let me know what you get. Remember, it's 10, click the NPR button, 4 equals. Looks like we agree it's 5,040, and that is correct. So there are 5,040 different ways to select that group of 4 people from that larger group of 10 people. Anybody have any issue with that or questions about that? Cool, let's keep going. Okay, so that was permutations. So now combinations are very similar, but again, combinations is the case where the order does not matter. It doesn't matter what order I select the elements, it just matters what elements I have selected at the end. So the formula for combinations is very similar, but the difference is that I have this extra little r factorial that shows up in the denominator. And the notation is different because now we're using a c for combination. So NCR is equal to n factorial divided by r factorial times n minus r factorial. So if we had 9 flavors of ice cream and we wanted to know how many ways we could make a double scoop, double means 2, right? Assuming we could select 2 different flavors, then the total number of things I have to choose from is 9. So that's the n. The total number I'm going to select is 2 because double means 2. So I would have 9C2, and if I plug in the correct numbers to the correct place in the formula, I get 9 factorial over 2 factorial times 9 minus 2 factorial. Real quick again, so first we'd simplify that expression in the parentheses in the denominator. 9 minus 2 is 7. Then we're going to write out what those factorials mean. Again, it means take that number and multiply it to every number less than it. Then we're going to cancel the common things on the top and the bottom. And finally, we'd be left with 9 times 8 over 2, which is 36. So there would be 36 different ways to have a double scoop of ice cream if there were 9 flavors originally to choose from. So that's the formula and how we do it by hand. Let's do it now with the calculator. So it's very similar. So this is the formula. On the calculator, please have it open. You're going to type 9. That's the larger value, the n. You're going to type the NCR button. It should be right by where you saw the NPR before. And then you're going to type 2, and you should see something that looks like this. And you should see the formula, the actual formula with the factorials appear up at the top. And then if you hit equals, you should get that number 36, looking just like this. Everybody get that? Anybody not get that, I should say? Yes, all good? Is there a reason I would not want to use the calculator for this? Not that I can think of. I mean, I guess if you, yeah, no. There's no reason. It's certainly fine to not use the calculator. Some people actually like doing work by hand because they just do, or they feel like they understand the like deeper concepts better if they do it by hand. But right, but there's no reason as far as like class or participation or your grade or anything like that. There's no reason to do it by hand. I do want you to know what the formula is, and I want you to know, at least in in theory, what's going on. But as far as doing the work, you can use the calculator. April, I see you're typing, so we'll pause to see what you have to say. James, you too. Is it because the calculator knows the difference between permutations and combinations that we don't do the multiply in the denominator? Yes, exactly. So notice, April, let me move this up. So see here, when you typed in the NCR, I'm sorry, the 9C2, see how it provided to you this formula? Like, you didn't type this part at the top, right? It just knew that this was the formula you were talking about, and it knew where to put what number. So you don't need to, it already knows what, it's like coded into the calculator that NCR means take the 2 and put it in these positions in this formula, take the 9 and put it in these positions, and then do the work. So yeah, it knows what the formula is, and it knows where to assign each number as long as you type it in the right order. James says some instructors want to see the work. That's probably why she asked. Yes. So I can't see your work anyways, right? I just want you to know how to figure it out, because we live in such a technology-driven world now. I think it's probably more relevant to you guys to understand what the concept is and to know how to use technology to find it. I think you all know how to multiply and how to divide. So by doing the work here by hand, all we're doing is practicing those skills that we already know and taking time, which makes us frustrated, and we're leaving ourselves open to having to redo problems because we can always make a mistake and then we have to start all over. If this were a traditional class and I could see your work, I might ask you to write down the formula or show some indication that you understand what's going on here at a deeper level, because then I could give you partial credit on your work. But here we can't do that, so why not use the technology to our advantage? Okay, sorry, now I got lost in the questions because I looked away from the screen. April says, okay, so the denominator is 2 factorial times 7 factorial, correct? Yes, that's right. Janet says, you still have to understand the word problem and what they're asking. Yes, exactly. So I'd rather you spend your time figuring out how to interpret a problem and then apply the correct steps with technology than to practice multiplying until you're blue in the face. Any other questions about anything we've done so far? Okay, so let's have you give it a try now. So you're going to get married, congratulations, and you need to pick 4 kinds of flowers for your bouquet. Gentlemen who are attending, it's going to be for your wife's bouquet, unless you want a bouquet, in which case that's fine with me. Anywho, so the florist has 12 kinds of flowers for you to choose from, and you want to figure out how many ways you can select 4 kinds of flowers from the 12 options. So the first question is, does the order matter? If you select roses and then tulips, is that a different bouquet than if you select tulips and then roses? Oh, congratulations, Raquel. Well, now you're going to know just how stressful it is that you're picking the right flowers because you have so many options. So the answer is no, the order does not matter. It just matters what flowers you have at the end, depending on the arrangement, but no, it should be a combination. Yeah, I guess you could have one predominant flower or something, but we're not going to get into that level of detail, but you're right. Okay, so what is the total number of things you have to pick from? Sorry, I'm trying to get the chat not over the question. Correct. So there are 12 total flowers to choose from, right? So how many do we want to pick? What's the total number of things we want to pick? It's 4, right? We want 4 flowers for the bouquet. Okay, so then it should be 12C4 4. So can anyone do 12C4 on the calculator and tell me how many combinations Raquel has to pick from for her bouquet? So no pressure, Raquel, but there are almost 500 different flower combinations you can pick for your bouquet. So 495 to be specific. Okay? Any questions about that or Raquel's bouquet? Just kidding. Good, Janet. Everyone really should feel smart. I mean, I think everyone seems like they're doing well. Everyone seems like they're getting this. Any questions about this or how to use the calculator for this? Okay. Well, that's it, guys. That's everything for this week. So if you understand the formulas for the dependent events, and if you understand the 3 types of dependent event questions that we did earlier, and you understand how to determine if a counting problem is a permutation or a combination, and then you understand how to get your answer for the counting in the calculator, then you know all the primary elements for this week. Jay says, I so overcomplicated this week. This helps so much. Oh, good. Yeah, I find that students making it harder than it is tends to be a really, really big problem in this class and in math in general. Sometimes it really is that easy, and we don't need to let some lack of confidence that we developed at some earlier part of life influence that. It really is that easy. Now, of course, there's going to be questions where maybe you have to combine different things we talked about today, or there's going to be different steps in it, but this is the hallmark, this is the foundation for everything you need. All the homework is going to be is applying what we did today to different scenarios. Oh, thank you, James. I'm trying to now remember. It's been so long since I watched the pre-recorded webinar. I can't think of what of who did it or what it was. But yeah, it's always nice to see a presentation from 2 people, because then you can kind of take the best of both worlds. Janet says, we will also use this calculator in weeks 7 and 8. Yes, so in weeks 7 and 8, we're going to be doing a lot of stuff with formulas, and the formulas and the steps are really not that bad. It's just kind of like plug the right number into the right formula. But the reason I like using this calculator is because, remember, let me go back real quick and show you something so I can, whoops. So remember when we were here and I was talking about how when we put in the formula into the little, the one-line bar, how the actual formula with the correct formatting and notation appeared up here. So that feature of this calculator is going to be super, super helpful in the next 2 weeks, because we're going to have these formulas that are not hard, but putting them into a single line calculator can sometimes get a little gnarly because there's a lot of parentheses you have to put in and stuff like that. So having the ability to see what it looks like before you hit enter, just to make sure everything's in the right place and you don't have like, there was a number that's supposed to be in the denominator but it's over on the side, or there was something that was supposed to be an exponent but it's in the denominator. It's just a nice way to visually check yourself. So anywho, yes, we're going to use this next week. Okay, sorry, I'm getting lost in the questions. Oh, good, Maggie. I'm so glad. Well, now you guys just making me feel so great. Any questions about the homework or anything from a previous week, or anything else you guys want to go over before you get back to your wedding planning, Raquel? Because we know you have a lot of flowers to pick from and it's going to be a big decision. Janet, if you do take more math classes, just remember that technology is your friend. Technology can do a lot for us these days, so that we can take away some of that grunt work that makes it a little long and tedious and just focus on what it means, because it actually is amazingly interesting and we can do a lot with it. It's just that those manual mechanical calculations that get in the way sometimes. Will any future exams go back to the previous exam info? No, so Math 130 does not have a cumulative final exam. So all your exams are just based on the 2 prior modules. So our next exam, which is due Tuesday of next week, is going to cover the probability stuff, so modules 5 and 6. And then the last exam will cover week 7 and 8, which is our financial math, and there's no cumulative final in this class. That's just the way it's set up. Well, I would encourage you to learn it and remember it, but you don't need to remember it for a final that's coming up later. Okay, folks, so if you have more questions, I will hang around and feel free to type them in the chat. Otherwise, we are all done. I'm going to stop sharing my screen for now. And you can go ahead and sign off if you don't have a question. Thank you very much for coming, and I will see you next week. And thanks everyone for being flexible about the day of the week this week. I appreciate it. Okay, Chase, did you want to go over it? Which one? 7? Okay, hold on a second. Give me a minute to bring it up. Okay, so let me share my screen again with you. Chase. This one? Okay, so remember the example we did about the TVs earlier? It's possible. So remember the one about the TVs? Yeah. So this is basically the same thing. So let me, how could we do this? Okay, hold on a second. I'm gonna see if I can get an image on D. Okay, so wait, hold on. So you got A through C and you're stuck on just D and C. But A and B are okay? Right? Yes. Okay, so let me just read it real quick so I refresh my memory. So suppose you purchased a digital music player and have 12 tracks, sorry, 12, why did I say 12? 8 tracks on it. After listening to them, you decide you like 3 of the songs. With the random feature on your player, each of the 8 songs is played once in random order. Find the probability that among the first 2 songs played, you like them both, you like neither of them, you like exactly one of them. Okay, so let me, hold on one second. I'm going to copy this and see if I can put it on the other page so we can write, because I can't write on that screen. Okay. So we have 8 songs total. There's 3 of them that we like. So that means there's 5 of them that we do not like. Do not like, right? So for letter C, it says you like exactly one of them. So liking exactly one of them means that you like one and you don't like the other. So that could go in one of 2 ways. So here's my 2 songs. 1 song, 2 songs. So this is the first song and this is the second song. So let's just say that I like the first song and that I do not like the second song. Okay? So let's do these one at a time. There's always, sorry, I didn't see that. You're saying there's 11 total? Well, yeah. So it gives you a different question just with different numbers, but it will go over the concept here, and then it should just be the same concept, but using the whatever numbers are in your question. You know, when you click on similar example, it gives you basically the same thing, but with different numbers. So for the first song, I want to like the first song based on the way I set this up. So what would be the probability that I like the first song? That's okay, I can't type either. So for the first song, how many songs do I have to choose from? Yeah, it's 3 out of 8. There's 3 that I like out of 8 total, right? Okay, so let's assume that one song has played now. That song is over, and I liked that song. So now the next song is going to play. So now how many songs are there to choose from, or how many total songs are left? Yes, exact. So, well, there's 7, right? But now remember, the second song, I don't like that one. So what's the probability that I don't like it? How many songs are there in the group that I do not like? Yeah, so this should be a 5, right? Because it's not that I liked the first and liked the second. I liked the first, so 3 out of 8, but I don't like the second. You were thinking of the other question. Does this make sense, though? Why it's 3 out of 8 times 5 out of 7? Okay, now what do I do with those numbers? Well, hold on, we're not done. So yeah, we're going to multiply, right? So this one we would get 15 out of 56, right? So cool with just that part? So that was specifically when I liked the first one and did not like the second one. But there's no reason why it had to go in that order. It's possible also that it could have gone like this. I do not like the first one, but I do like the second one. That's possible, right? So let's do it this way now. And we're just going to just keep the previous one in mind. So what's the probability that I do not like the first one? Yes, 5 that I don't like out of 8 total. Okay, so the first one played. Now what's the probability that I like the second one? Yes, 3 that I like out of 7 remaining, right? Okay, and I multiply these, right? Same rules like as before. So again, notice it's the same. Again, I get 15 out of 56. Okay, now when it said I like exactly 1, I could have liked exactly 1 this way, where I liked the first one and didn't like the second, or it could have happened this way, where I didn't like the first one, but I did like the second one. Now, when I saw that word or, think back to last week, when I saw that word or it was implied that word or in my sentence, what did I do with my probabilities? Remember? Exactly. We added them, right? So if I did 15 out of 56 plus 15 out of 56, that should be it. Let me go back. So this is that answer right here, 0.536. Okay, so on your calculator, do 15 over 56 plus 15 over 56. You should get 0.536. Why was it 3 out of 7 and not 3 out of 8? Right here? So at this point, it was 3 out of 7 because remember, after the first song has played, there's only 7 songs left. So there's only 7 songs here in the total left over because the first song has already played. And of those 7 songs, there's 3 that I like because the one that just played, I didn't like it. So there's still the 3 that I like remaining in the shuffle. Does that make sense? Excuse me. Okay. Chase, does it make sense? Awesome. So letter D is basically telling you just to redo the songs, but assuming that, hold on. Redo A through C if a song can be replayed before all 8 songs are played. Okay. So basically, so like in this guy, let's pretend we were doing this one, but under the conditions of letter D. So, okay, we wanted to like the first song and not like the second song. Okay, so on the first song, there were still 3 that I liked out of 8 total, right? So that would still be my probability of liking the first song. But now, when we get to the second probability for the second song, let's assume that that first song that just played, now it can repeat. So there's no reason why we have to exclude that song that just played from our total anymore. So now, assuming that song can repeat, what's the probability of that second song being one that I don't like? Well, there's 5 songs that I don't like, but now it should be out of 8 because that song can replay. So I don't have to take it out and drop that denominator down to 7 songs left. I always have 8 songs that can play. So it's going to be the same steps, but your denominator is going to change. Sometimes your numerator will change too because you don't have to remove songs after they've played. Does that make sense? Cool. Did you want to go through it, or do you think you have it with that explanation? Okay, cool. Still stumped, or it's more clear now? Okay, got it. Yeah, so it's just that change where if the song can replay, we don't have to keep changing certain numbers because we've removed one. There's never one removed. Any other questions, you guys, about the homework or what we went over? Anything from a prior part of class or anything else? Yeah, C was what we did when we did the 15 over 56 times 15, I'm sorry, plus 15 over 56. That was letter C. That's okay. Anything else you guys want to go over? We like your company, James. Okay, cool. Thanks, Chase. All right, I don't see any more typing, guys, so I'm going to stop sharing my screen again. Like I said, if you have a question, go ahead and type it. If you don't have another question, you guys can feel free to sign off.